So it's the to the right. So what happens? Increases. If you were to push the bar, you'd still get a current. Not counterclockwise, but clockwise. And if you're pushing the bar and pushing the bar, you'll be happy with the flux. Be going down. Importantly, in both cases, the flux is changing. The flux is changing through the loop. And that is the main idea that will allow us to generalize this toy example that's easier to think realistic, to more general scenarios, is that you generate current flow through a loop if you change the flux through that loop. So if the flux through the loop is changing, in this case by increasing the area or decreasing the area, you'll be able to generate a potential difference, which will cause charge to flow. So, this leads us to the last idea of the day. Tomorrow will be dedicated to practice with this idea, both with the lab equipment that we didn't get to today and some practice problems. And this is called Lenz's law. And Faraday's law. There's actually two that we're talking about here. I should have written those in the other order, so we'll talk about Faraday first. So first, Faraday's law is the generalization of the motional EMF idea. And EMF created by a change in magnetic flux through a loop. So it's taking the same idea of the motional EMF and generalizing it to thinking about what's happening with the loop itself and the field. We can't. Yep. Go ahead.
I was just going to use Lenz.
Lenz, we'll get there in a second. Lenz talks about the direction of the current flow in the loop. Lenz's law will help us predict is it clockwise or counterclockwise around the loop. So Faraday is there is a current. Lenz is which direction will the current flow. First, I want to derive a general expression for this. So if we start with the result we got for a motional EMF, and we think about how much extra area we're going to add on to that. The way we're going to do that is by looking at V to the right. And V is going to be delta X over delta T. Times B. We're going to do a little bit of regrouping with this. L times delta X times B over delta T. If we go back to our picture, and remind ourselves that L is this height, and delta X will be how much distance we go to the right. What is L times delta X going to give us? the area. Specifically, not the total area of the loop, but how much extra area we've added in. So I'm going to call it a change in A rather than just A. So that's equal to the change in area times B over delta T. And we looked at a static field, but the B field could be changing too. So another regrouping will give us delta B times A over delta T. And what's magnetic field times area? Flux. So that leaves us with our result here. That's the strength of the potential difference is your change in flux over time. So it's the exact same law, kind of just generalized to work beyond the specific example we've talked about. We'll save a lot of things. We'll save lots of let's do a quick recap. I think that'll be useful. Law tomorrow. And we'll do practice until Tuesday.